Yep, it does. Remember, you can't bring noisemakers.
We were booing them too, and everyone was like, what if Russell gets mad? And we're like, what's
I'm torn on whether or not, because there's a point where school spirit becomes heckling, and then it's not in sportsmanship anymore. Unrelated, last thing. Do you guys know who Bruce Lee was?
Yes.
Who?
He was my martial artist.
I don't believe you. So he's a martial artist, and he was an actor, right? And he was like one of the best martial artists to ever exist. You guys agree? Like, I don't really know enough about it to say whether or not that's true, but commonly renowned as such. Check it out. I learned something about him this weekend. Everybody has some demons or some baggage that you have to carry around with you. Do you guys know what Bruce Lee's favorite drink was? Water! Yeah.
That's a good.
I did not make that up. I wish I'd had. Anyway, here we are.
Say like Red Bull or something.
Here we go. Notes. What's up? We're going to start some notes. So I can't physically make you write, but I can make you look like you're at least going to write stuff. So you need paper and pencil. We are starting 4.3 today. Fun fact, this is the last section of chapter 4.
Where's the newspaper?
Yes. I like it. I like it. Okay. 4.3. We are going to look in this section over a more specific glance at this idea that we've touched on in a couple different sections. We're going to be looking at the conservation of energy. Now, these ideas, we've seen them. I was shocked when you guys mentioned that you had seen the 3 blue, 1 brown videos. Blows my mind. Don't know why on TikTok you guys would get these super high-level math videos presented to you. Don't understand it. The algorithm's crazy. But you guys have maybe, how many of you guys use TikTok? Okay, cool. Nobody's found my channel yet, which I appreciate. No. Furthermore, though, check it out. Have you guys seen the? I'm just going to show the video real quick. It's a short. It's on YouTube. Let's see here. 3 blue, 1 brown.
Whoa, I know that.
Okay, so this guy's videos. And let's see. I'm just going to search pi because when I referenced this the other day, you guys all recognized it.
Let's just watch the video.
We're not watching the whole video because it goes way beyond what is our focus. How many of you guys have seen this guy? I don't get it. I don't get it. So,
I think I saw an ad for this video, or like this video popped up somewhere.
yeah, I don't know. He must fund it or like pay to promote it somewhere because I don't understand.
Videos over it, like the blue and the brown thing like popped up, and I thought it was about eyes.
Yep, it does look that way. This guy, why it blows my mind that you'd all heard of him is he touches on things like math subjects in a really great way. He's phenomenal about it. But even the videos, they're entertaining because the animations are great. But beyond that, he gets into math like pretty quickly that's near or above what I'm capable of grasping just on my first watch through. I watch his videos when I feel like I have a math itch that needs scratched. Like if I just thinking, man, I haven't done any good math or been challenged with it lately. These are the videos that I watch. But he touches on conservation of energy here right at the beginning. Now, we're not going to watch the whole video because I assume about this point is where people aren't going to understand what's going on anymore. But I want to pay really careful attention to one comment that he makes. We have to be quiet though because he's not the loudest voice.
Velocity from the
Oh my
light.
gosh, okay, he has a really loud voice now.
While the second one starts out stationary. Being overly idealistic physicists, let's assume that there's no friction and all of the collisions are perfectly elastic, which means no energy is lost. The astute among you might complain that such collisions would make no sound, but your goal here is going to be to count how many collisions take place.
That was all that I needed, was that one little part. And I just want to touch on that last part again. Like, let's...
And all of the collisions are perfectly elastic, which means no energy is lost. The astute among you might complain that such collisions would make no sound.
No energy is lost, which means no sound. Even sounds themselves release energy. Now, as we go through here, we're talking about the idea of conservation of energy. This is pretty crazy. Does that seem like math to you or physics?
Physics.
It feels more like physics, but there's certainly some math there. Now, for those of you that haven't seen this, he's just changing these blocks. He's letting it hit. There's no friction, so there's no energy loss there, nothing fighting it. And they just click together until they no longer touch anymore, right? Okay. If you've seen the video, don't spoil it. We'll watch like another minute.
Take place. So, in slight conflict with that assumption, I want to leave a little clack sound to better draw your attention to that count. The simplest case is when both blocks have the same mass. The first block hits the second, transferring all of its momentum. Then the second one bounces off the wall, and then transfers all of its momentum back to the first, which then sails off towards infinity. 3 total clacks. What about if the first block was 100 times the mass of the second one? I promise I will explain to you all the relevant physics in due course. It's not entirely obvious how you would predict the dynamics,
count 'em.
but in the spirit of getting to the punchline, let's watch what happens.
1.
The
Ready to
second
count?
one will keep bouncing back and forth between the wall and the first block, like a satisfying game.
That's right. It's 31. Good call. Okay. We went from 3 to 3-1.
In total, there will be 31 collisions
Cool.
before each block is sliding off.
It did, but this is never going to catch up.
Again.
So they're splitting the energy. He's going to make it heavier. Count these again.
In that case, there would be quite a few more clacks.
No way.
That's so. Ew.
Adding up the numbers to 313 total collisions.
313. So
Actually, hang on.
I think he's going to go one more.
For it.
Oh, 314. Cool. So you've probably, nobody went to the YouTube video and watched the rest of it, so you have no idea what's coming here. Last one.
This is with all of our crazy ideas and conditions.
3,000.
Yo,
No way.
what year?
Resulting in
You actually.
3,140.
So
3,000 is a lot.
have you seen this video? Okay.
It's forgivable.
So if you want to see that, I'll go as slow motion as I can here with a
The
million.
first block was 1 million.
Once we're here, and I'll just go super slow motion if possible. Yes. Okay, try to hustle.
What would it look like on 2 times?
We'll be done by then.
Yeah. Then again.
Oh,
With all of our crazy ideas and conditions.
So, obviously, it's going way too fast to even see it. But love the fact of what was just seen there. This is not what we're doing other than the fact that the only thing I needed that video for was to say, hey, look, he specifically talks about how he adds the clicks so that we can think about it. The clicks wouldn't really happen if this were no energy being lost. But Carson, you noticed something. It was 3, and then it was 31, and then it was 314, and then it was that number. I bet the next one would be this. Seemingly, this is a terrible way, but an effective way to calculate pi, which where that connection gets made, I think is super interesting, the fact that it does. We will cover different things. In here, we're not a math class, but we celebrate a holiday on March 14th. We gonna do Pi Day in here. It's a thing with me.
I thought there's 100 days.
So pi is, what's pi? 3 point.
3.14.
Okay, stop there. 3.14. What's March?
March is the 3rd month.
Hey, so the 14th of March is 3 point. We celebrate Pi Day. It's during spring break, the Friday before or the Monday after. You guys can bring pies. We'll talk about pie. We'll do all sorts of math with pie.
Pie?
Yep, absolutely you can bring pie. I'll bake a pie. Anyway. Gross. Yes, we can eat pie in class.
Banana pie.
Ooh, we can eat our pie at 1:59 on March 14th.
Why? What's that?
3.1415.
Oh.
And 1:59:26 even, we could do it. Yeah, we'll get real pie. Anyway, if you guys are kind of into math, that dude, what did you just do? Is it a paper cut? Gross. That's not the right word for it, but all right, check it out. We're going back on. Right off the bat, our main focus within conservation of energy is this law, the law of conservation of energy. And this is like the wordiest definition I think that we have all year. The law of conservation of energy. Okay. As we look at this, this is a fundamental law or rule that the universe follows. It has to follow it. Luckily, we've been able to investigate this and have a pretty good grasp on how things work, but it can be simplified real simply, like super easy. Energy cannot be two things we can never do. Whoa, energy. There's a G in there. Energy, good. I heard cannot be destroyed. Good. Cannot be created nor destroyed. So particle accelerators are real, but you're not creating nor destroying energy. Never. You cannot do it. The most important thing, and it's easy to get goofed up, cannot be created nor, and I'm going to make that look like a O like it should, destroyed. There's an obvious issue that people have with this. We burn fuel at the powerhouse to do what? Do we really though? That's what I'm after. Even at the powerhouse, we burn fuel, right, to heat up water. We're not getting rid of energy. Somebody's blowing up right now. Whoever it is, please silent. Okay. The following point here. As you're looking at this, cannot be created nor can it be destroyed, only converted. Now, when we look at the powerhouse, and we haven't talked about this type of energy, but there's a whole nother type of energy that we just haven't discussed. We burn fuel. And we burn fuel to change that energy, that chemical energy in the fuel via this reaction of burning it. It then heats up the energy. It changes from chemical potential energy to thermal energy. That thermal energy then changes to thermal energy in water, which then uses that energy to vaporize the water to make steam, which goes up and converts to mechanical energy to turn that thing to make our electricity. There's nothing that's been magically created in the process. We're just taking it in one form and changing it and changing it and changing it. No matter what, that's all that happens. Go ahead. Somewhat. Similar line, yeah. Okay. Now an easy way to think about this. Only converted or transferred. We have an example already of this from the other day, but it's nice to hit it again. On that quiz that you guys took the other day, the last question, I claimed you could do it without any math. If we imagine a scenario, and I'm going to say step 1, step 2, step 3. So they're going to be just little pictures. Consider. And I'm going to drop a ball. We're just going to say, here's the ground. So this is the ground that we're after. Okay. Hypothetically, don't care the height that we're at. Let's say I have a ball right here where the velocity is equal to 0. Okay. Somewhere, and this is similar to our egg drop, but we see right here the velocity is equal to, if it's down here now, it had to move, right? So give me a number. I don't care what it is.
5.
So 5 meters per second. And then all of a sudden, right before it hits the ground, it's going faster still, right? Velocity is equal to, maybe it's 10 at this point. Everybody agree that this is what would happen if we drop this ball. So check it out. Before we drop it, if we're only looking at potential and kinetic energy, is there any kinetic energy here?
Yeah, no.
Kinetic energy might be equal to 0. Why? It's not moving. Velocity squared is 0 squared. There's nothing. Okay? Which means all of the energy is what? Gravitational potential, but you're right. And I don't have a mass or anything, so let's just make up a number. Let's do 50. Okay. At this point, if the velocity is 5, maybe, just maybe, the kinetic energy is like 25 joules. Which what would the potential energy be? So it'd be 25, right? How about down here? And
5? Oh, just 6.
so we couldn't ever get to 100. Love that I heard that, though. It might have even been misspeaking, but I'm okay with that. Somebody mentioned 100. Why can it not be 100? Why can't the kinetic energy be 100 right here?
That's more than the potential energy.
The maximum we had this whole path was 50, right? That was what we started with. I can't make more than that. That would, like, destroy this law. So if we look at it, that's fine, really. If we look at it, maybe because I'm about to hit the ground, 48, and potential energy would be what then?
2.
It would have to be 2 joules. Now, there's one more step that I just didn't include. When it hits the ground, there's no more potential energy, right? And it hits the ground and comes to a stop. There's no more kinetic energy. It wasn't destroyed. What happened?
It dispersed on the ground.
It dispersed. 1, it sends shockwaves to the ground, absolutely. 2, if you drop something, will it probably make a noise?
Yes.
So there's some of your energy. If you drop something really big and really fast, like an asteroid is an easier example. What do asteroids, if you drop something really big, really fast, it hits so fast that it starts to heat up the stuff around it, right? Like asteroid left a huge crater. Man, some of that's turned to heat, some of it's turned to light. Like all that energy gets turned into something else, but it's not created, it just gets moved. Okay, this idea is super fundamental to the understanding of physics. Now, as we go through stuff, when you hear people and political season is over essentially because the presidential election just happened, so thank goodness for that, first of all. But the second thing is during election time, you often hear people talk about conserving energy because, you know, all the policies that relate to it. As we're going through here, people might say we're running out of energy. No, can't happen. We're not destroying the energy. We are running out of usable forms of energy. Like, sure, that happens, but the language there does mean something different. So, looking at this, can energy be created? I can. Can energy be destroyed? No. Okay. Cool. Big idea, important idea. Vincent, I know you can't make your lead quieter, but can you press less hard? Well, there I can't hear it anymore. Somebody was scratching lead really loudly. All right, we're going to switch to purple. Now, moving forward, is that enough, Sabrina? Sorry. Okay. So, going through it, when we look at these, then the big question, we can't create, we can't destroy, that's fine and dandy. We should look at energy transformations, because this is really where it all gets used, or changed anyway. Energy transformations. Okay, we looked at a few different types of energy the other day as we went through stuff. Give me some examples of types of energy that we saw. You even had to give me examples of how they get used in your life on the quiz the other day.
Wait, what kind of energy we talking?
Yeah, sure. There's kinetic, so that's not a type. There's elastic potential energy. Kinetic energy, there's what? Gravitational potential energy, chemical energy. Like all these get used, right?
Wait,
Now,
was it called physical or what?
it wasn't called physical,
It was-
although we're flirting with that idea here. Okay, we talked about the power production. We heat up water to make steam that turns a turbine, right? Now, when we make something physically move via this energy, we are talking about a very specific type, and we're going to sneak in, that shouldn't be there, this should be a subsection, sorry. Mechanical, I can still hear it. We're going to define for ourselves mechanical energy. Now, your guys' favorite class is obviously mathematics. That makes sense. I get it. When we look at this, I'm going to teach you guys some math notation that I just want you to be aware of, but we're not going to use it. Cool. I might use it. I like it. It makes writing stuff easier. Mechanical energy. When we look at energy, oftentimes, again, we're focused on transforming it from this type to another. Often, it's mechanical energy that we're after. So, when we look at this, it's super easy to define. You just have to be able to add stuff. That's it. We're going to define mechanical energy as the sum, which sum means I'm going to do what? I'm going to add. It's the sum of all potential and kinetic energy in a system. In a system. Now, underneath, because people lose this sometimes, here we go. In this includes two different types that are easy to overlook. Includes elastic and gravitational potential energy. And I'm going to use PE as mine. You can write the words potential energy if you'd like. When we talk about mechanical energy, we're just adding up all the kinetic and all the potential energy. Now, somebody the other day asked a great question. Would you ever find the amount of chemical energy in something? It's a big question. That's a great question. We'll see how people calculate it. We can actually do it in here. Couple things else that I'd like to learn. Shorthand stuff, love it or hate it? Okay. The sum of stuff. If we wanted to write this out, we could write the mechanical energy. Mechanical energy. And this is just going to look like a formula for a second, but I promise, like, I'm doing this to at least expose you to some cooler math stuff. Mechanical energy is the sum of all what?
All potential kinetic energy.
So if I just wanted to be really concise with this, do you agree with that statement? Okay. Are there any other types of energy that weren't listed here? I hit kinetic and potential,
Elastic.
but it's chemical potential, right? And the elastic potential. Now, we haven't written them down, but we did talk about it. You burn fire, which is a chemical reaction, to change it from chemical to something else. Why do people burn fire ever?
Gas. Oh wait.
Light.
Heat.
Light.
Heat is energy and light is energy. They're both energy. Notice those aren't listed here because heat and light don't physically move stuff. Heat can have consequences that make it happen, but it's not the heat itself that's moving it. So as we're looking at this, just so you guys know, have you ever seen this Greek letter?
I've seen it.
Okay, so this, there's no way to avoid it. You guys are going to relate it with something else. This is a sigma. It is. Okay, specifically, it's a capital sigma. What's the word sigma start with? S. And the word sum starts with a? Oh my gosh, this is just how you say the sum of stuff. The sum of potential or kinetic plus potential. This is a capital sigma in the Greek alphabet. Normally, people draw it like this if you want to be lazy. I think it looks much nicer if you commit to actually making it look nice. Your choice. Anytime you have to write the sum of stuff, that is a useful shorthand to use. Cool. All right, so we get mechanical energy. It's just all these. But I want to make one more little statement. Notice that total energy, and I'm going to stress this one more time. Are there other types of energy than kinetic and potential? I gave you two examples a moment ago. Do you recall what they were?
Yes.
What were they?
Light. Heat.
Light and heat. The total energy is not equal to mechanical in most cases. Which one's bigger? Mechanical energy is smaller. Total energy includes light and heat and all those things. This is the bigger value every time. Now, cool. We are unlikely to ever completely conserve mechanical energy. Can you think of any situation where we would lose either kinetic or potential energy in a situation?
The Earth explodes.
Okay. Can you elaborate a little further? Maybe.
Like gas, carbon, gone. Evaporate.
Okay, you're right. I don't know that I love the easy connection
No,
to
actually,
it.
no. Water.
I have a random fidget spinner here. I'm going to go ahead and add some energy to it right now. So I have chemical potential energy waiting, right? Because in my body there's energy that I'm waiting to use in my muscle to move my finger. Okay, I just added energy to it, right? Okay, it's going. Is it going to go forever?
No.
Why? I thought we could destroy energy. Hey, we lose this energy pretty commonly in the form of friction. Beyond that, close your eyes for me real quick. Is it still spinning?
No.
Yes.
No.
Yes.
Yes.
How do you know?
I hear it.
Oh my gosh, it's losing energy to make that sound through friction, and all that stuff is happening at the same time. We can see that energy is lost. That statement is going to conclude, I'm going to put an asterisk there. We struggle to conserve all mechanical energy. And it's for those two reasons that we just highlighted. If I went and got some WD-40, would it spin quieter and for longer? But would it spin forever still? No. Have you guys ever seen an Euler's disc? Okay, I'm going to go to Miss Forfietta's room at the end of the day. I'm going to try to find one. We struggle to conserve all mechanical energy. Oftentimes we struggle. Now, going through here, we've already talked a little bit about that transition between potential and kinetic energy. Pretty easy to highlight with projectile motion. If we launch a cannonball, we're going to launch it up into the air. I don't think you even have to draw it. I'm about to launch it. After it launches, most of the energy in that cannonball is what sort? So I lied. You don't have to draw it, but we should talk about it. Here's a cannon. It's an old-fashioned one with that, and they have a stand there, and there must be somebody here, like, loading it up. Okay, here's a cannonball launching out. At this point in the launch, most of its energy is what?
Increasing.
So there's, I don't hate any of those words. Is it mostly potential or mostly kinetic? Okay, I would agree with that. How about up here? Now, is there still some kinetic? Because it's still moving forward, but it's mostly potential, right? Okay, how about down here when it actually hits?
It's still gonna move around, right?
So we'll say it's like the instant before it hits. So it hasn't quite hit, it's almost there. But it's like almost all kinetic, right? Like essentially none of it is gravitational potential at this point. We see it changing in that situation. Okay, we will conclude tomorrow Euler's disk. That's what I'm going to bring tomorrow to show you guys the weirdest thing ever. It's not really the weirdest thing ever, but cool. Carson, don't forget what we talked about. Cool. 30 seconds, don't leave yet, but I appreciate you guys.